Audio check, 1, 2, 3. Okay, audio sounds okay, which means we can get started. Ladies and gentlemen, welcome to the stream of the Discourager of Hesitancy. We have started a mini lecture on programming fundamentals or something. Just some thoughts I've had about programming, and I don't know if it's all in the right order or divvied up right yet. This is kind of my first time putting all of the thoughts down on paper and presenting it. So, hey, Pat. Yes, this is the Doe, the Discourager of Hesitancy. Welcome, welcome. How's your New Year's starting out? Yeah, been a while. Christmas, New Year's. Can always spot Doe. Nice. Yeah, here we are. Yeah, we're starting a little bit of a mini series of short lectures on beginner programming for my nephews, basically. So none of the long rambling, no prep, just do it coding series we've been doing. Yeah. So we're going to do this mini series for, I don't know, probably all of this week. I think I've got enough topics for 5 mini lectures. Gustavo G. Fanelli, welcome, welcome. How are things going in Brazil? I don't know about you, Pat, but the weather here has been warm and rainy and muddy. We've only gotten snow like once. El Sai Kangaroo, yo. How are things in Quebec? Doing fine here. Good, good, good. Glad to hear it. Everybody's compilers and languages doing well. It's like 25 outside right now. Oh, that's a little cold. Snow on the ground. Okay, okay. So at least you got some weather. Code KO. If they can't do category theory at 10 years old, just change them. Oh, category theory. We probably aren't going to touch on that in this beginner series. This one's a little bit more targeted for my nephews, so I'm quite happy now. Just got my Atlas regions rendering working. Nice, nice. Super cool. Yeah, once you get Atlas rendering, like you can do Atlas textures, a lot of things become possible that are pretty cool. So, nice work. All right. So, here we go. Mini lecture starting up. Feel free to ask questions or interject comments as I go. Sometimes I'll go a slide or two before I remember to check the chat, so just pipe in and I'll get around to it eventually. All right. So let's see here. If I do this right, we can turn off Emacs, turn on the old browser. I'll attach the slides to the YouTube video when I upload it, so you can always go get the slides yourself later. In the meantime, let's get started. Assuming I've got things set up. Yes, all right. Did I update the labels correctly? Yes, okay. So today we're going to talk about some technological periods, informational vocabulary, some fundamentals of programming, things that weren't pointed out to me when I started in a clear, concise, easy way. And then we'll go through how to learn a new language. We kind of got you started with a GCC compiler yesterday and your Hello World program. Whoops, number 5 is not a thing. All right, we'll fix that before I post them. All right, technological periods. If you follow the wiki link, you'll find that prehistory, we had the Stone Age, we had the Copper Age, the Bronze Age, the Iron Age. Early, ancient history, we had some different periods. So what period are we in now? And the answer is we're in the information age. And I find it interesting that we're in the information age, and the number of people who can tell me what information is vanishingly small. Even among programmers, the concept of information isn't clear in a lot of minds. If you look at these technological periods, they are periods where a new technology forces the way society works and the balance of power is managed, right? People hit each other with sticks, and somebody figured out you can use a rock, and you can use rocks to make tools, which means your food production is more efficient. Turns out that rocks break pretty easily compared to other things like copper or bronze, so you upgrade your technology, you can kill more efficiently, you can harvest more efficiently, that sort of thing. And we went through an industrial age, and we're in the information age now. So the technology that has forced society to change the most in recent years is definitely the information technology. But what is information? So we're going to go through some vocabulary because I think discussing these words will be very helpful. I will use them over and over again. Mostly I'll use them correctly. There are some that have slipped into common usage, which I will use incorrectly knowingly. But let's go through it. So information. Information is the answers to yes or no questions that provides an answer to a question. Wow, that needs to be edited quite a bit actually. Well, no, that's fine. It's fine. We'll just roll with it. Provides the answer to a question or resolves or reduces uncertainty. All right. So when we're talking about entropy, like black holes or thermodynamics, it's all related to information. When you're talking about cryptography, right, how to hide your message so other people can't read it, that all relates to information theory. How much power do you need to to transmit how much information? Well, that is all about information theory. It all kind of started with Claude Shannon in the 1940s or so, about the same time that Turing was kicking around doing the basics of computational theory, right? Theory of computation. Kind of on those two is built all of what we have today, and other contributors as well. I would love to dive into the history around the development of the computer and modern information theory and all of that, but that's outside of the scope of this discussion. So when I say, information, I'm talking about this. Yes, no questions that answer a question or resolves or reduces uncertainty. So sometimes your question isn't answered directly like yes or no, but are we close, or are we closer than this much? So you can reduce uncertainty. So a bit, we always talk about bits and bytes and megabytes and all that stuff. In this case, a bit is a unit of measure of information. It is one yes no question or one yes no answer. Okay? If I say the word 32-bit integer, that tells you I have 32 yes or no questions or 32 yes no answers about that number. So a parameter is a characteristic that defines or classifies a system. I'll come back around to how this connects a little bit. But for example, if you have a point, if you want to describe a two-dimensional Cartesian coordinate plane, a point on that is defined as having two parameters, an x coordinate and a y coordinate. If you're talking about a complex number, that has the real and imaginary parts. If you're talking about a three-dimensional vector, that has three parameters, x, y, z. If you're in homogeneous coordinates, it also has a w component, so it's a 4-vector, right? We parameterize a system, and each system can often be broken down more and more. So when I talk about a parameter, it's a piece of information of some number of bits that defines or classifies a system. Data, then, are the values attributed to those parameters. So just because I told you a two-dimensional Cartesian coordinate point has an x and y parameter, it's not data until you tell me what x and y are, right? At the point that x and y are 0 and 0, now we know we're at the origin. That is data. Data is values attributed to parameters. Okay? So when we say, hey, send me the data, it means we expect a certain number of parameters, which is information transmitted in bits, and we know what those parameters are and how to map those values to those parameters. Okay? So when I start saying things like data and parameter and bit, there are meanings behind those. Encoding is how we decide what the yes-no questions are that define a parameter. Okay. Travest, hope you're well today. Yes, I'm doing great. You really like this new format? Good. Yeah, we'll probably do this through this week. I've got probably 5 mini lectures planned, so this is the second one. We'll get through this week and see where we go from there. But yeah, dedicated to my nephews. They all say they want to learn programming until I try to tell them what programming is really about. So anyway, informational vocabulary, encoding. So when I say I have audio encoded in PCM 16-bit signed integers, that tells a programmer everything they need to know to understand each value, each of those datum, each of those data. There are other encodings. We can talk about those in a bit. A message is a collection of information or data, all right? In this case, we're going to refer to a lot of things as messages by different names. So a common message we might consider would be an HTTP packet, which is a whole bunch of information about your web page and routes and timings and quality of service, and then the payload to your browser that says, here's what you should display and how you should display it, and here's how you can interact with it. So maybe an HTTP packet sent over a network. But that's just built on top of a different kind of message called, TCP packets. And they all have a bunch of data that they have to carry around. But we also store files on a computer, and that's another kind of message, maybe sent through from your terminal or from a text editor to the disk, and then retrieved off that disk. So that's another message we pass around. Files, network packets, intra-process communications, all sorts of things that we can do, shared memory, are ways we can pass messages. And in fact, a lot of message passing can happen inside of programming language without ever leaving the program itself, where you're passing pieces of information from one part of the program to another part of the program. So messages. A format is how we understand what that message contains. So when I say that we have a WAV file format or an MP3 file format or PNG, those are all the rules for how we build a message, what the encodings are, what the bits mean, right? So if we go back to, let's not go back. Okay. A protocol are the rules for how messages are communicated. You don't have to deal with a lot of protocols when you're opening and closing a file, except you do have to tell your programming language if you're reading the file or writing the file, or if you're appending to the file. So there are still protocols there, but like networking has a lot of protocols. You have UDP, which is very simple. It's just, hey, send a bunch of data, and hopefully the guy on the other end receives it. To TCP, where sequence numbers, quality of service, recovery protocols, handshaking, all sorts of things can happen in a protocol. So there are a lot of examples of each of these we can talk about. For example, encoding. Let's go ahead and just take a look at some encodings. We know the ASCII encoding, right? Let's see. There we go, Wikipedia. ASCII has 128 code points, so each character you want to represent is represented as a number. So the number 0, the digit 0 is represented in 7 bits. Okay? That's not actually the best picture. Let's see. Blah, blah, blah. But ASCII is not the only one. Does anybody else know an early competitor to ASCII? These days, a lot of times UTF-8 is a very popular encoding. But back before ASCII took over, you had EBCDIC, which looks a bit different. Here we are. There it is. There's EBCDIC. The printed characters are here. The numbers are there. It's a completely different layout from ASCII. So that's a little bit about encodings. So if you wanted to move from lowercase a to uppercase a, you'd have to add some amount. Same thing for any of these letters here. Any of the alphabet letters can be made uppercase by just adding a constant. Same thing with ASCII, and it's a different amount, right? We have floating point number encodings. Those are floating point, float. IEEE what? Well, they don't have it as standard. IEEE 754. When we have to agree on an encoding, there's a standard that says here are the rules, right? So here's an IEEE encoding. Usually they blah, blah, blah. Oh, come on. There it is. This is basically the easiest way to understand a floating point encoding. There's 1 bit for sign, there's 7 bits for exponent, and then there's the remainder of the bits for the mantissa, or the fractional part. And all of the rules for how you understand the bits for a float are well defined in the IEEE 754 standard. And the more you understand about a format, the more you can use and abuse it, right? So there are things you can do with floats once you understand this representation, what the bits actually mean. Even though I started to learn how to program over 10 years ago, this is a really nice refresh for me. Good. Glad to hear it. I'm trying to be like informative, but not too overwhelming. So we'll see how it goes. Like I said, this is kind of my first time putting these thoughts into a lecture format. So it may be a little disorganized right now. I think with a little practice and a couple of refinements, it might actually be useful. So thanks for being my guinea pigs, everybody. So that's encodings. Formats, we can look at different ones, right? There's a PNG format. It's how you store an image. Okay, and let's see here, blah, blah, blah. Here it is. Let's see here, file header. So this is the format, right? We have to agree on all of the bytes and what they mean inside of an image. So there's a hex value up front. There's these 3 letters. For some reason, there's a DOS-style line ending. Oh my gosh. To detect DOS line ending conversion of the data. Terrible. So on and so forth. Then each chunk has as many bytes. And here's how you understand a chunk. Different kinds of chunks, right? Look at this. Look at all this standard. Yeah, some of these things I haven't thought about for some time. Yeah, a lot of times we throw on words like, format and encodings and don't think about it. So it's good to have that memory. So if you want to store text or times in your image, here's all the pieces you need to understand. So here's PNG. There's a bunch of different things. In fact, probably some of the most interesting parts of PNG as a format is their 2-stage compression process. Very interesting read. Not really necessary to this discussion. MP3. How do you store audio? Well, there's a format for that. There's a standardization. There was a lot of hoopla about patents. So yeah, the more you know about your encodings. Yep, here's your header description. All the bits have to be defined. Bit rate, frequency, padding bits, what mode you're in, stereo or mono, etc., etc. And then it has different encodings you can use. So pretty cool. The more you learn about this stuff, the better programmer I think you'll be. So that's encoding the message. Code KO. It's difficult picking the right topics to teach someone new. Yeah. So at this point, I figure if I expose them to the vocabulary and the ideas, we can blow through them pretty quickly, but they can always come back to the slides and refresh as we talk about things. So we've talked a little bit about encoding, file formats, protocol. Okay, let's go look at a couple of protocols. Lots of options, right? Transmission control protocol, TCP, segment structure. So here you go. Here's everything you need to know about TCP format, right? This is a message. And here's how you have to define the data for the other side to understand it. If you're going to communicate with somebody, you have to speak the same language. So, English speaker and, Japanese speaker need a common language. So you have to agree on which bits on each end of the communication are happening where. Same thing for loading a file. You ever got a file and it's like, oh, this is corrupted data. It's like, it means that the computer didn't understand something, threw it off. The agreed upon information was not where you expected it, or you don't understand what this format is, and then you got a corrupted file maybe, or corrupted network packets, checksums. All of this is part of that protocol, and it can get very complicated. Like this is not that complicated, but like just staring at this doesn't reveal to you why every piece is here, even though every piece of this is important. You'd have to study TCP for a while to really understand the full protocol. Most of us use it and ignore it, but knowing that there are all these rules is a useful starting point. If nothing else, to teach humility, right? As a programmer, we often use abstractions without thought. And when you start digging in, you suddenly realize, wow, everything I use is built on so many layers, and each layer you understand just opens whole new worlds of understanding what's happening under the hood. So while we're not going to dive into these protocols and codings, formats right now, we will talk about these things in more detail as we go through different topics. So there's some vocabulary around information theory and around programming that we're going to use a lot. So here's the clear definitions, a couple of simple examples around most of them, and we'll talk about them in greater detail later. I completely avoided web dev and JavaScript. I know nothing about it. I approve. I did do an unfortunate amount of web dev once, and I'm not going back. So, all right. So, fundamentals of programming. People ask what a programmer does, and it's the process by which you described the simplest of tasks in the greatest possible detail to a stupid machine. One thing people don't seem to understand is that computers are not smart. You're not computing with something intelligent. The only thing a computer can do is what it's told. So when it fails, when it does something unexpected, it's because somebody told it to do that. Intentionally or not is a whole different discussion. But programming can be very difficult because you have to break down tasks in ways that you wouldn't with a person. Right? A person can infer, a person has context, a person can learn in ways that machines simply cannot. Even modern AI, that's a whole separate lecture. I don't know if I'm going to get to that this week or not. Even AI doesn't cover what a human can do. Okay? So a lot of programming is about understanding what the computer expects and how to tell the computer everything it needs to know to do the job right. And where programming fails happen is in the programmer assuming things that the computer doesn't, or the person giving the wrong instructions or the wrong information to the computer, which brings us to lovely Charles Babbage, kind of the first person to conceptualize a general purpose computer. And he did design a general purpose computer, electromechanical, general purpose, programmable computer. which with the technology at the time he could have made functional if his funding hadn't run out. So, the guy is not stupid. But yeah, if you put in the wrong information or the wrong instructions, will the right answer come out? So, with humans, you can often, the human brain will auto-correct certain things or can infer certain things and arrive at a correct answer, even given wrong inputs. But a computer just isn't that good at it. So, little exercise. And I saw this on the Tim Kaine video. It was an excellent little exercise. How do you explain to a computer what a cup is? Anybody? Feel free to try it. How do you define a cup? There's a good little video. Maybe I'll just throw the link to that, unless people are really interested in working through it together. Let me, while I'm waiting for any inputs, if there are any. Oh no. No, OBS, you lost my mouse again. Dang it. The difference between formal languages and natural languages. Yep, one is for people, one is for computers. Computers like formal things. They want all the rules, definitions. Where is it? Come on. I gotta get my mouse back, I'm afraid. Let me see. Let me see here. How to go about this. If I don't share my browser, I go hunt up this thing. It was an excellent little video, and it was just like perfect timing. He's talking about exactly the topic at exactly the right time. Where is it? Just a moment. I should have put the link, but where was it? That or I'm not. Maybe it was further back than I remember. I'm not finding it now. Pretty sure it was Tim Kaine. Maybe I'm thinking the wrong creator now. Anyway, try to define a cup. You'll find it a very difficult task, because anything you can dream up that defines a cup, you know, it's a concave, three-dimensional shape that holds water, right? Well, then is a swimming pool a cup? Then you're like, oh, well, it holds between, this much and this much liquid. It's like, okay, well, is all the different things that can make it a cup, right? Does it have a handle? Does it not have a handle? What size is it? What is it made out of? All the different things you can think of to define a cup are fuzzy. A cup is a fuzzy concept, and humans learn to attribute cupness to things that look like other cups. Now, modern computers can do this to some degree with modern machine learning, but it's not quite the same. They only have an image to work off of, right? Whereas the attributes of the cup are far more involved than just that. You have feel, you have smell, and not just cups. I'm talking about all sorts of things, right? You have so many inputs as a human, and you can fuzzily group things into categories that a computer can't reasonably, and then can be shown something nowhere near your training set or your data set that you grew up with and still identify it correctly as a cup, right? Another interesting thing is with human language, humans tend to define things differently. So depending on their language, right? So what one culture might call a chair, another one might have a separate word for, and actually have the concept of chair broken into different concepts that you and your language do not. Or, for example, English has a special word for pale red, which is pink, right? But other languages don't have a word for pink. They just say pale red. Meanwhile, other languages will have a specific word for pale blue, which English doesn't have. You have to say pale blue, right? So different colors, different categorizations are very natural language dependent, right? So that's one of the problems. How do you identify things to a computer? Well, that can be a very hard problem. 2, how do you explain steps to a computer? You want to make a sandwich? Okay, we'll tell a computer how to do that. So you say, well, you get the bread out of the cupboard. It's like, wait, what's bread? So you describe bread, which comes back to this problem. Then you say, now, And then it says, okay, I understand what bread is. Maybe we get to that point, sure. And then we say from the cupboard, and it says, well, I don't know what a cupboard is. So now you have to describe what a cupboard is. And then it's like, okay, I know what a cupboard is. Where is the cupboard? And now, like, how do you define where the cupboard is? Do you give it GPS coordinates? Do you say relative to the front door of the house, or relative to the location of the computer, or there's a million different ways you can define these things. And then, slice the bread. Well, how thick? On which axis? How do you orient the bread? Who's holding the bread? How do you hold the bread still while you slice it? What should I use to slice it? What's a knife? I don't know what a knife is. What does slice mean? How do you slice? All of that has to be described to a computer. So when you talk about programming, like this is what we're trying to do, is describe a sequence of actions, like this making a sandwich, to something that's too stupid to even know what bread is. And just because a computer can look at a picture and say, I think that's bread, and be right 99% of the time, does not mean that a computer knows what bread is. It knows how to recognize an image of bread. So this is kind of what we're talking about. A computer is unbelievably stupid. If it's doing something wrong, it's because a programmer somewhere, or the hardware fails, a programmer somewhere told it the wrong instructions. Okay? So that's programming. Teaching a stupid computer to do something simple. Now, there are tools we use to break this up. One is sequencing. When you start out, this is probably the best mental model for this, so we're going to stick with it for quite a long time. But a computer executes one instruction at a time, then moves forward to the next instruction in the list. So there's a sequence of things to do. That's the easiest thing to think of when you're talking about programming. So when we're talking back here about making a sandwich, there's a sequence of actions. Get the bread out of the cupboard. So, well, where's the cupboard? Okay, move to the cupboard, open the cupboard, take the bread out of the cupboard, close the cupboard, move back to the counter, right? Now we've got a sequence of 5 actions. Put the bread on the counter, okay? It's a sequence of steps. So sequencing is very important. A lot of times, thinking through a programming problem is about finding the right sequence of actions. But sometimes you need to make a choice. Sometimes there's a branch. So instead of going to the next step in the sequence, you can have a choice of, do I go left or do I go right? Maybe there's 2 loaves of bread in the cupboard, and you have properly told the computer how to identify 2 loaves of bread. It may ask, which bread do I use? Well, now there's a rule. You have to set a rule and say, maybe on Tuesday and Thursday, you use the wheat bread, and Monday, Wednesday, Friday, you use the white bread. That's a branch. So on some condition, we go do this sequence, and on this condition, we do that sequence, okay? So branching. Sometimes we need to be able to jump to a different part of a sequence, all right? Looping. One of the main reasons for computers is because the thing that they're really, really, really good at is doing the same thing over and over again. Humans kind of suck at that, actually. So, replete, that's wrong. What humans are really good at is intuition, working with ill-defined systems, partially defined requirements. We're really good at filling in gaps, taking a guess, adjusting. Computers suck at that. If you tell a computer exact set of instructions and say, do that a million times, the human would get bored, the human would wander off, the human would start making mistakes. The computer does not. Looping is where your branch says, go back to the start of this subsequence. Okay, go do these 15 steps over and over and over and over again until there's a branch that says jump out of the loop. Okay, so we have sequences of instructions. We can sometimes choose to do things or not do things, moving around in the program, in the sequence, and a lot of those special branching has to do with loops. A lot of it. Okay, decomposition. So when we're talking about building the sandwich, we took the simple concept of making a sandwich, which as a human would be you don't have to describe the individual steps to even a child as young as 5. You say make a sandwich. Maybe they can't handle the knife, maybe they can't reach things, but they understand the steps of go to the cupboard, take out the bread, put it on the counter, right? They understand what has to happen. They break this problem down into steps, and you have to break down every step for a computer. So decomposing your problem is one of the major fundamentals of how to think through a programming problem. Algorithms are finite sequences of instructions that can solve a specific class of problem, okay? Examples are if we have a whole bunch of data and we want to put it in order, right? We want to know what the hottest day of the year is. Well, there's lots of different ways we can do that. Each of those is an algorithm. Here's one. Let's say that we want to find the hottest day of the year. We take all the data for all year. We just have one number per day, 365 of them, and we walk through and we just say, is this current thing I'm looking at, is it higher than the last highest thing I knew? If it is, then we take that value. And then we move on to the next one. Is this one higher? Is this one higher? We can go through the whole thing one time and find the highest value. Okay? But maybe we want the top 10 warmest days of the year. Well, maybe then the algorithm is we need to put all these temperatures in order, and then we can just walk over those last 10. Well, how do you sort them? That's a sorting problem. Okay, there are lots of algorithms for that. Very well studied program. How do we find the least common denominator? How do we find the greatest common multiple? How do we find the next prime number? How do we update the physics engine in a game so that things can collide, and what happens when they collide? What's the physical response to that? Those are all algorithms. A lot of algorithms already exist and can be found and learned. They're just known sequences of actions that you might use to solve a specific type of problem. But a lot of times you'll also find that your situation doesn't quite match an existing algorithm, or you need to compose smaller algorithms into larger algorithms to make everything work the way it needs to. So we decompose the problem, we look for known algorithms or adjust a known algorithm or build on multiple common algorithms into a more complex algorithm to solve our real world problems, okay? And sometimes you invent your own algorithms, which is kind of fun. And then lastly, we're going to talk about a little bit about abstraction. And this definition is a little abstract, which is fine, but it basically means if we have a very specific case, a lot of the times we want to pull out the common elements and put them off to the side and say, irrespective of these factors, this part is common to all these types of problems, okay? Then we can solve this problem and then put it back in that domain where it was. So we can pull it outside of its context, solve it separately, and then put it back in its context. Or you know, yeah, I guess, like I said, we'll come back and discuss abstraction in greater detail on other lectures. So hopefully those are some fundamental tools a programmer needs to learn. Let's see. So let's just look at them real quick. Sequencing. Let's see. Hey, C-Films, how are we doing? We're doing good. We're doing good. How are you doing? We have Azzurro for light blue in Italy. Okay. Okay. Nice, nice. Yeah, so like I was saying, defining things in natural language is so much different from defining it for a computer. So if we're going to learn how to program, we learn to think about things in sequences, branches, loops. We decompose problems into their smaller and smaller pieces until it's something we can define for a computer, because the smaller we break it down, the easier it is to define. Algorithms are sequences of instructions that solve specific problems. And then we have to abstract our problems in ways that are very strange, unusual to the rest of the world. I'm not doing 100%. I'm sorry about that. What's the matter? C-Films? What's going on? Oh, you're sick. It is that time of year. That's too bad. I am sorry to hear that. Not fun. Standard cold or something more serious? Cold or flu? Those usually aren't too bad, just miserable. Well, hope you feel better soon. That's no fun. I'm trying to get over it. Yep. Get lots of rest, drink lots of water. So learning a new programming language. You should always, if you can, work from examples of code. One of the things I liked about the 3 languages we worked on last week or two was they all had small pieces of code examples. Those are great for learning. But you have to ask yourself these sorts of questions to start learning a language. What are the primitives? All right, let's see. I think now is the time where we start switching back and forth. If we turn off the browser and we turn Emacs back on, we're going to go back to here. We're just going to start playing around in here. So what are the primitives? A primitive is the fundamental data you can work with in a program. So in C, you have things like int, x, and y, right? You might have float temperature, maybe. You might have a character C. You might have booleans for, is thing true. You might have, let's see here, I had a note somewhere. AK Elements, hello, hello, how are you doing? How goes the what is it, the built-in profiler for Onyx, built-in performance information? How's that going? Built-in profiler, that was it. I think most coding languages based off of C have 5 concepts: variables, conditionals, loops, arrays, lists, and functions. Yep, that is pretty much it. And we'll get to each of those. So this is a mini lecture series I'm kind of doing for my nephews. They keep asking, hey, blah, 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 programming this, programming that. So mini series on basics of programming. It's running but missing scopes in the timeline view. Yeah, I've only ever profiled pieces of systems or used existing profilers. Building your own profiler, I could see being a very difficult task. Documentation is a bit minimal on the one I chose. What'd you choose? I'm going to actually skip forward just a little bit. We're going to go to documentation. So I like C++ myself, but this is also a perfectly valid reference. So here's 2 references I've linked. So here's a C reference. If you want, let's see here. Keywords, I think had a decent, doesn't really break them down by type. Anyways, you see here, micro profile gives you a profiler view in a web page, opens a web server in your application so you can remote profile from a separate machine. Yeah, interesting. Cool. Also means you don't have to worry about the display. So, nice. Makes it nice, especially if you create an app for a phone, you can profile it from your PC. Yeah. Remote profiling is definitely nice if you're going cross-platform. That's pretty cool. But bad documentation, huh? All right. Super cool. Okay, so primitives. We're going to build up our program based on primitive values. And those are most of the primitives: integers, floats, characters, boolean. We also have pointers. We'll talk about pointers eventually, but there's a pointer and another type that's associated with it. So in this case, this means it's a x is a pointer to an integer. So pointer is kind of its own special type. Okay, so primitives. What are the basic building blocks to build values and store my data and associate that data with parameters to make, or values to parameters so that you can have meaningful data? All right, so there's some of the parameters. Back to the old browser. Okay, so question 1, what are the primitive data types? All right, integers. Oh, did I? No, that's not what I wanted. There we go. Integers, so int, long, short, unsigned. This all tells the compiler information about the encoding. So most modern hardware, I believe ints tend to be 32 bits, signed. A long tends to be, well, a long int. Anyway, I don't use these most of the time. Long or short or int. I tend to do something else in C, which we can get into. Unsigned says this integer can only go from 0 and up. It can't go negative. So it means that it's represented a little bit differently in those bits. So, and we aren't going to talk about specifically integer numbers today. Floating point numbers, floats are 32-bit, doubles are 64 bits of floating point information. Character, unsigned, and you can have an unsigned character, which is an 8-bit integer, basically, because of ASCII and a pointer. So those are the primitive data types. How do you store a value? In C, I've already shown you the declare a variable. Now we need to be able to assign a value to a variable. So let's hide the old browser. Hey, what's up? How's it going? How you doing? What's up? We're doing a little mini lecture series on basics of programming for my nephews. We're talking about declaring variables. So you say what type it is, then you give it a name, and then a semicolon. The semicolon is like a period at the end of a sentence. Just tells the computer this is the end of an idea, an end of a statement or an expression. Okay? So here's how you declare a float. Here's a floating point temperature. Here's C. So the question is, how do we store a value here? Actually, let's call this picture. If you want to store a value, you just say the variable is assigned the value something, right? Y is equal to negative 13. Those are integers, easy to do. Temperature equals, 31.5, right? We can use decimals now. 27, doesn't matter. Character C, so C could be equal to, capital Q. These are all the primitive data types in C and how you would declare them and assign them. Boolean is not really a data type in C, but we can kind of ignore that for now because most compilers will take it, or at least GCC takes it and works with it just fine. So is true equals false. You have the values true or false if you want. Assigning a pointer. The pointer is an address to something else, so we have to take the address of x. So x is an integer, and we want the pointer to have the address of x. So address of x. Again, we'll come around to pointers and deal with them more in the future. These are how you assign values in C. You can also declare and do the assignment all at the same time. So we could do x equals 5, y equals negative 13, temperature equals 42.135, character C equals Z, single quotes for characters, that's important, and the address of y. Okay? So in this program, it tells the compiler, I need enough space to store an integer named x, an integer named y, a float named temperature, and here are the values they start with. Then when we come in here, these values overwrite these values. So a code file usually executes top to bottom, and declarations matter. The order that the declarations happen in matter. Yeah, so here's declaring a variable, assigning values to variables, overriding variables, and that sort of thing. There's a lot more to it we can go into, but this is like a high-level overview. So, do you not need F at the end of floats? Let's see here. Let's see. Hold on. Let's see here. Haha, what? So your sleep schedule is good again? Oh, what's up? Cool, C23. Yeah, I don't know if I'm going to get too much into the differences between the different versions of C. I tend to keep it fairly C99 except for booleans. Do you not need F at the end of floats in C? Need? No. It will downcast a double to a float, so it's not strictly necessary. But yeah, we can be more explicit. That's fine. Double height, right, equals a bigger number, right? Maybe like 9265358979323. So yes, technically a float has an F at the end and a double doesn't. But again, at least in GCC, a lot of the times it auto casts the floats and the doubles to each other. Casting means that you take something that's one representation and you turn it into another representation. So I could take this integer x equals 5, and I can do this, and it will say, well, I know what 5 is as an integer, and I can turn that into a float that also has the same value of 5 in it, even though it's a different representation. Usually we are explicit about that and tell the compiler, I want this type, which I know is not a float, to be represented as a float. That's called casting. But yeah, I've never had any problems with auto casting a double down to a float in C. Other languages are more strict about it. Depends. 4 a.m. here. Jeez. So it's approaching good. 6 hours of sleep. I'd prefer 7 to 8 hours. Yeah. Well, good. Good to get some sleep. That would be double literature by default. Maybe compiler will warn about narrow casting from double to float if you write it too big and have no warning. Yeah, maybe if I enabled more warnings, it would show up. Maybe that's just me because I worked for 12 plus years with warnings as errors. Yeah, that's fair. That's fair. A lot of settings options that make the right things quiet and the other right things loud. So good to point out. Good to point out. Thanks for pointing it out. So we'll put the F after the floating point number. Okay, so that's kind of how you deal with the primitives, how you declare a variable, how you assign a variable, and declaration and assignment can happen in the same statement. Okay, where were we? Browser. So if you're learning language, what are the primitives? How do you store a value? How do you combine primitives? In C, you have 3 major ways to combine your primitives, and they all do slightly different things. You have an array, you have a structure called a struct, and you have unions. Now, I tend to forget things that I don't use as well. Yeah, exactly. C++ is just too complex to remember every nitty details if they're not useful. Yep. Agreed. Which is why we're starting with C. A lot less complexity for a beginner, and it still maps very well onto the hardware. You have to understand what's happening on the computer with your C to do good. So let's look at an array. Maybe we can declare an array. An array means we have a whole bunch of the same type of thing in a row. And again, I'm going to say things that are slightly true, slightly untrue, and we're just going to deal with it for now. So let's see here. If we want, we were talking about using the temperatures, right? So we would have maybe a float temperatures, and we could tell the compiler how many we want. We want 365 temperatures, 1 for each day. So this tells the compiler is, I want a big block of memory, 365 floats next to each other all in a row in memory. Okay, so that's one way we can combine primitives. We can take a whole bunch of things and put them all in a row. So maybe we have temperatures, maybe we have humidities, and have 365 of those. That's one way we can define one way we can define combined data. Wow, cannot type 365 pressure, right, for atmospheric pressure. And to access a value, we would use the subscript arrays, right? Temperatures on day 0, humidities on day 0, and pressures on day 0. So we can say float day 0 temp, float day 0 humidity, float day 0 pressure, right? Maybe that's one way we want to store and represent our data, right? So we want the 0th element on temperatures. If we wanted to get day 3, or day 13 of the year, we'd access the 13th element of each of these arrays and stuff it into a variable that tells us enough about the thing. So let's talk briefly about naming. Notice that my temperatures, I don't know what that means. Is it in Kelvin? Is it in Celsius? Is it in Fahrenheit? The computer doesn't know, doesn't care. It's just a number. It's a float. It doesn't know what the word temperature means. It doesn't know what humidity means. Is that absolute or relative humidity? Is it percentage? Is it as a percentage or as a fraction? So in other words, is it between 0 and 100%? Or is it the humidity as a ratio of moisture in the air to the rest of the air content, and therefore, 0.35? It's not the percent version, but the fractional version. Pressure. Are we talking about atmospheres? Are we talking about pascals? What does it mean? The computer doesn't know, doesn't care. These names are for the programmer to understand and communicate the idea to other programmers. By the time the computer gets done with this code, the word temperature does not exist in your executable at all with respect to this variable. Oh, I'm hiding the darn thing. Let's see. There we go. Screen is not swapped. Yes, thank you. So, yeah, here's your arrays. Temperatures, 365 of them. You can get the 13th day's temperature. You can set the 13th day's temperature, right? So we can do temperatures 13 equals, maybe we go with Celsius. Well, maybe it's just winter and it's Fahrenheit. You don't know. Humidities, maybe it's, maybe we have it in percentage, 35%. Or maybe it's a very rainy day, 95%. Pressures on day 13, maybe it's a low pressure day. So instead of 1 atmosphere, it's, I don't know what pressure is. Anyway, so here's how you declare an array, you assign to elements of an array, and here's how you read a value out of an array. Okay? So that's one way we can represent data, is in an array. We can also represent data in a struct. So maybe we have a structure how C-like do I want to be? I kind of don't, but struct weather. Maybe it has float temp, float humidity, float pressure. So now we've said here are 3 different things that are all associated. So maybe we put in something like this. Let's make this a little bit more complex. Bool, did rain 365 days worth, and did rain number 13 equals true. High humidity low pressure. So day 13 did rain. Okay, so we can, the array has to all be the same type, but inside of a struct, we can mix and match our types. So bool did rain. So now we have a data type called weather, which will contain all of these things. So a struct is one way to combine different types of data. So we can say a variable named weather, which we'll call weather 13, or day 13 weather, be consistent. And then we can set the different fields. So we can say the temperature equals day 13 temperature. We can get the humidity, day 13 humidity, day 13 pressure. Okay, pressure did rain. So we can do things like this, where we can say, here's a day's worth of weather, and we can just pass this whole day around as one thing. It's no longer a primitive, but it's still a data type that describes everything we need to know about that thing. So instead of an array of temperatures and an array of humidities, we could instead do something like an array of weathers. We could organize our data this way instead of 4 arrays of the primitives. We'd have one array of a compound data type, if that makes sense. Okay, so a lot of programming is about deciding how your data will be represented and accessed and modified. So like I said, there's lots of different ways to do things and lots of different tricks for managing it. So this is just a couple. So you have arrays, you have structures to combine different types of data. You can take arrays of structures. You can put structures in arrays, maybe like a character array for the name, right? So we have a 256 character name. So maybe day 13 weather dot name. Maybe it's just empty. It has the 0th character in it, an empty string. Lots of things we could do. Okay. Okay. Then we have a union. I don't know if I want to talk about unions in this stage of someone learning to program. You even ordered the members correctly. Love it. Thank you. Thank you. Although no, probably something more like that. But also, it depends a lot on what size the Boolean is. I've actually found a lot of architectures use Boolean as a 32-bit integer, basically. Yeah. Anyway. So this says, structure this data all next to each other in memory. So the temperature value is right next to the humidity value, is right next to the pressure value, is right next to 256 bytes of characters, is right next to a Boolean. So these are all happening in order. There are things about padding we could talk about, which AK Elements alluded to, but we're not going to talk about that today either in detail. All right. Union. Do I want to talk about unions? Do I want to talk about unions? I kind of do, because I think tomorrow we might start using a union. A union. Do I want to start talking about unions? Is a way to interpret the same bits of data as different types of things. I don't think I feel like talking about unions yet. But it is a way of combining information. Okay, so let's do this. Union float int. This is just an easy, simple example. Float, float int 32. Maybe we do that. So what this does is it says create enough memory to hold the biggest thing here. Maybe it's a float, maybe it's an integer. In this case, they're both the same size, so maybe we even just do something weird. This doesn't make any sense in a programming problem. But this says take the biggest thing here and create a record of that size. So in this case, weather, which contains a float, is already as big as this thing, but then it has another float, so it's bigger. The biggest thing in here is a weather. So every time you ask for one of these union of floats and ints, float int, it creates a record as big as this thing, because this is the biggest thing. But then I can do things like UFI dot float 32 equals 7. But then I can ask questions about the integer representation of those same bits. So I can do UFI dot int 32 plus 3, or maybe we do this. We do and 0 7 1 2 3 0x 1 2 3 4 1 2 3 4. There we go. Maybe we do something like that. This, again, it doesn't make sense in context, but these are the kinds of things you can do. So you can say, this memory, give me the piece of it that, give me these bits as though they're a float, and assign that -7. Now take those same exact bits, represented as an integer, and we're going to AND it with something else, right? So maybe we take UFI.float 2 equals that. Well, can't really do that. We can do this. So we can say, taking these bits as an integer, we're going to AND it with this number, which basically means flip that top bit to off no matter what, and then shove it back in. And now if we were to print out UFI.float 32, we should get something like +7, because we flip that top bit. Okay? So we can take things as floats, treat them as integers without changing by just changing how we represent it in our usage. So these are the same bits. Float 32, int 32, those are the same bits. We can just treat them different ways. We'll get to where that's useful in the future. Oh, wow, changed my view here. Good heavens. Must have hit a keyboard shortcut. There we go. So there you go. We have arrays, we have structures, and we have unions. Most of the time you're going to stick with arrays and structures in C, but we will use a union. So, okay, back to, there's an assumption that int is 32 bits. Maybe use int 32t. Yep, that is true. I mentioned I don't actually use things like int or long int or short int very often in my programming. Typically, this means 16 bits. And by typically, I mean it depends very much on what hardware you're running and what compiler you're running. Long int is 32 bits, and regular int is 32 bits. And long int tends to be 64 bits. Again, all of this is hardware dependent. A character tends to be 8 bits. So what I usually do, what What's Up is talking about. No, I mentioned earlier I don't use the basic data types very often in C. I tend to do what's an include of std int, and instead of char, if I'm talking about a number, unless I'm talking about an actual character, I'll use that. But if I, instead of using short int, I'll use int 30, int 16t, and you know what? Let's line this up. It'll be easier to read. Instead of this, I'll tend to use int 32t. This one's the same, actually, now that I'm thinking about it. And then this one is 64-bit. So if you include this library, it defines these types the same way that you would with, so instead of me using short int when I'm in 16 bits, I can actually just say, this is a 16-bit integer, this is a 13-bit integer. So if I include this thing, it means that down here, he's correct. I would use int 32t. And now it's for sure definitely the same size. If you're on a different computer, especially if it's embedded, maybe long is 64 bits, or maybe on a modern computer, it's decided that a basic integer is now 64 bits, in which case long might not mean anything. Or maybe they decided it's 128 bits. You know, it depends on your compiler, it depends on your hardware. So he is correct. If I include standard int .h, it defines this, so I can say it's a type underscore t type of integer 32-bit integer. We did talk briefly about unsigned, so there are also unsigned versions of all of these, where all you do is put the word unsigned in front. And it means this can't go negative. And all we really have to do, again, this is fairly common pattern, I think, 32-bit, 64-bit. We can just put a U in front of this and it tells us the same thing. So uint 16, so if I start using these things, so especially for like uint 8, sometimes I do want things as bytes and not as characters. I might do something like that. So yeah, just a little more explicit, a little bit more clear, a little easier to understand, I think, in a lot of cases. Okay, so that's how we combine data types. Dum 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 dum. Where are we? Where's my browser? I lost it. There it is. Okay. So how do you combine primitives? We talked about that. How do I manipulate values? So we have operators, we have built-in functions, we have common library functions, and there's a bunch of them. So we'll just go through a few just to get a little bit comfortable with some of these ideas. And actually, it's as well defined. Long is not guaranteed 64-bit. Yeah, the size of any of those is not guaranteed, I don't think at all ever. The size of these things is never guaranteed. Char, I believe, is always 8 bits. I've never seen an architecture where it wasn't. But short doesn't mean 16 bits. It just tends to be 16 bits. Int doesn't mean it has to be 32 bits. It tends to be 32 bits on most of the systems I've worked on. And yeah, unsigned long does not have to be 64 bits. It's just most of the systems I've worked on, it is, but there's no guarantees. Whereas these things do have guarantees. If you say uint 32, that's what you get. It's always 32 bits. So I tend to use these more. But that brings us to operators. So if we want to change values, right? Does that make sense? Maybe we want to compute float chance of rain equals temperatures on day 5, or day 5, chance of rain. Let's stick with day 13. We can do this all sorts of different ways, like I said. So we can say day 13 chance of rain equals our day 13 weather dot temperature times day 13 weather dot humidity. And I'm 100% sure this is not a correct equation for guessing chances of rain. But we can do things like multiply two values together. So here it multiplies temperature and humidity, then it will multiply that product with pressure. We can add, subtract, so maybe it's plus 13. We can subtract values, minus 0. We can divide by all sorts of stuff. Doesn't matter, okay? So operators are things like this: multiply, add, subtract, divide. We can do bitwise things, which I kind of showed here. It means take the bits of this and AND them with that, which we'll talk about bitwise operations more later, but you can AND or XOR, you can do NOT. And what these do is it says if two bits are both 1, that's a 1 in the output. Otherwise, it's a 0. And OR says if either bit is a 1, then the output is 1. Otherwise, it's a 0. Only if both of them are 0. And XOR says the output is 1 if one or the other value is a 1. Again, we'll get into bitwise operations a bit later. And a NOT says if I see a bit that's on, I flip it to off, and vice versa. So we have arithmetic, we have bitwise, we also have Boolean logic. So if we're asking a question, right, if we want to branch, if day 13 weather, temperature is less than freezing, right, in Celsius. This less than is a comparison. We have less than, we have greater than, less than equal to, greater than or equal to. Those are all things we can check. We can ask equal to, we can ask not equal to. But we can also do Boolean. So maybe we do an AND day 13 weather dot is did rain. So AND means both of these things have to be true to continue into this if statement. We can also do logical OR. So it's kind of like these bitwise ANDs and ORs, but not quite. So if the temperature was not 0 or it did rain, we do something special, right? So that's so arithmetic, add, subtract, multiply, divide. We have bitwise. We can go into more operators as we use them. I'm just trying to get some categories into heads here. We have comparisons, less than, greater than, equal to, not equal to. And then we have the logicals. Let's just write those all out. So we have arithmetic, bitwise, logical, comparison, something like that. 4 major categories of operators. Chandu 16, hi, new to coding? You have 15 years of experience. I'm trying to teach. Yes, my nephews have asked me to teach them some programming, so I'm making a short beginner series videos. Assignment subscript error operator. That's true. That's true. So assignment operators. So we did talk about assignment a little bit, but I didn't say it was an operator. He's correct. So when I set this field temperature equal to this value, that's an assignment operator. So we did it up here too, where we assigned an entry of an array to a value, this assignment operator. And then he said the subscript operator. So that's this thing where we said the 13th element of this array that says temperatures of this array. This operator says get the 13th element of it. So we can use that subscript operator to assign to an array or to read out of an array. Okay. We'll talk about what these arrays are actually doing with memory later, but for now, yes, assignment and subscript. And in fact, there's a special kind of assignment called what's it called? Modify and assign, maybe something like that. Subscript. So assignment is the equal sign, subscript is some number. This is C, so we're not going too crazy with C++ stuff. Lucky nephew, you have to show him some algorithm solving. We'll get to that. We'll get to that. I figure there's enough other tutorials to do certain types of things. I want to approach it a little bit differently, so we'll get around to all sorts of things here. We can have plus, we can have minus, we can have multiply, divide. We have the remainder operator for modulus operations. We also have negation, which is an arithmetic thing. That's probably most of those. Modify and assign. So we can plus equals. So that says, let me give you an example of this one. If we have the variable x, we can say plus equals 13. And that's really just the same thing as x equals x plus 13. It's like a shorthand. So you have plus equals, minus equals, etc., right? So you can modify a value and assign it at the same time. Comparison, talked about that a little bit. Less than, greater than, less than or equal to, greater than or equal to, equals, and not equals. Those are the very common comparisons. Bitwise operations, we kind of talked about that. We have bitwise and or XOR and not, which again we'll talk about in more detail later. And we have logical and logical or. Okay. I think technically this is also an operator of, means member of. Member of is dot. So some structure dot field variable equals value. Array, then you tell it what element you want. I think that's getting closer to most of the important operators in C. There's a few that we can still talk about, but this gets you pretty good in the operators area. Okay, built-in or library functions. One thing you might want to do is include math. And now all of a sudden you have things like sine of an angle, cosine of an angle. You might have power. If you want to, you also, let's see here, raise the 4.5 to the 1.5 power. You also have exponent for raising e to the power of 2.3. All sorts of functions coming from C, which is one of the reasons I have those links. Where's the thing? If I show the browser, so in C++, if I go to any of these libraries, like CMath, these are all library functions that I just have access to if I pull this, if I include math.h. I get cosine, I get all the trigonometric functions, I get hyperbolic, exponentials, logarithms, powers, square root. I get a square root function, that's very handy. I can, yeah, so the reason we have a documentation link is so that you can find the function you need when you need it. Blah, blah, blah. So these are some built-in functions. You've already seen a couple for stdio we talked about. We talked about printf. So here are the functions that are provided. So if we go to printf, which we've already used, it comes over here. And there's a lot of usage about this stuff. And then, so here's an example, right? You can output characters, integers. You can format your integers in different ways. Blah, blah, blah. Floating point numbers, they always get some interesting tricks. It's star. Oh, that's actually handy. Okay, good to know. So there are lots of built-in functions, reading files, outputting text, reading text, scanning through text. Here's standard int. This is, like I said, where it defines these special types so that I can know exactly how many bits I'm using. Standard library. I can turn a string into a float, etc., etc. We'll use those actually eventually. Random number generation. All sorts of things. Most of the time, C math and C standard input, output, and standard int are the most common ones I use. Oh, and C string and C time. Those are probably like the top 5. Anybody else? What do you think is a great beginner language to teach people? Aha! I'm glad you asked. That's actually part of a different lecture. Let me do this. Dun, 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 dun. Where's the... I don't like Google Docs in some ways. Where is it? We'll just go in here. Slides. There we go. Yesterday, not that one. Part 1. Yesterday we talked about that very thing. Pick a language. I recommend C and Lisp. Even if you never use them, if nobody pays you to use them, they change the way you think about programming. To use C, you have to understand what the machine is doing with your code on the CPU and in memory. For Lisp, it teaches you about recursion, that your code is just another form of data. You can modify your code because it's just data. Data and code are interchangeable. Like, they change the way you think about programming. But I'll also say, it depends on what you're trying to accomplish, right? If you want to be a hobby programmer or you just want to build a web page, I agree. Python, JavaScript, those are great. A lot of times you'll have like electrical engineers or mechanical engineers who don't care about programming itself other than it as a tool to solve their specific program, in which case maybe, Fortran is the right answer. In a lot of cases, yeah, Python and JavaScript are, well, I would never recommend JavaScript. JavaScript is a terrible language. But Python's fine in a lot of cases. But I would say if you want to dig deeper and improve yourself, I would say C and Lisp, even if you don't use them in a large professional product. Haha, agree, JavaScript is the worst. No, I would not say JavaScript is the worst. I would say Perl holds a special spot in my heart for being darn near the worst language ever designed. AKA, no web dev for me. Yeah, no, well, and here's the thing. If you learn what the machine is actually doing, because you've used C, I think a lot of people would start to realize what some of the things wrong with JavaScript are. But yeah, I don't want to do web development. I don't like how many layers are between me and the hardware. I think C is like the best layer to be at for productivity versus you're on the metal, you're able to really control a lot. So that's my opinion. And again, it depends on what you're trying to accomplish. If you're a web dev, learn your JavaScript. That's definitely the most important language. If you want to do hobby programming, I agree. Python's great. And in fact, I'll use it for prototyping a lot of stuff. because it's so little work to type something to getting a prototype working. But I think if you really want to learn deeper, C and Lisp will change the way you think. Okay, so we're learning a new programming language. How do I manipulate values? We've got built-in functions. We've got operators. We've talked about common library functions a little bit. Looked at the documentation a little bit. Some different libraries that are available to you. So then the last thing is, how do I make a function? So in C, a function is pretty straightforward. Let's make a function called, and this is a stupid one, so it's going to be void add, or not void. Let's do int32t add int32t a to int32t b. So this is what we call a function declaration. We declare, we are telling the compiler somewhere in our code, I will tell you how to do this. This is a function called add, which will have two parameters, a and b, and this is what kinds they are, int32ta, int32tb. And I will return this type. Now again, the compiler doesn't know what add means. So I can do anything I want, and it doesn't care. It doesn't know what this means. That's for me to know. And when I implement this, I give this name so that the other programmers, and so I can in the future know what's going on. So we can then, somewhere in our code, it doesn't matter too much where, we can do it down here below. We can actually return a plus b. Okay. So what that says is, I have this value a. You're handing it in. You're handing me this value b. Here's what I'm going to do with them. I'm going to add them together and return that result. So this int32 is what's being returned here. And if we wanted to use that, we just make a call. We could say int32t value equals the addition of 13 and 42. Right? We would expect value to then hold 55. We don't have to use a constant here. We can use ufi.int32. We could use day 13 weather dot something. I guess we don't have an integer in there. Well, we can take temperature and cast it, right? Because we can do that. Temperature temp, and tell it, take that floating point number and turn it into an integer. In which case, I don't remember what we set it to. What was it? We set it to 23. So then this would be 7. Well, it wouldn't be 7. It'd be some weird number. So we can use all of these values and pass them as parameters into a function. That's the basics of functions. You don't have to declare and define your function in different places. You could do it all here, right? Return a times b. If you do this, then we'll have two definitions for the same function. That's going to be unhappy. So you just have to be a little bit careful. The order that things happen in matters. I can't use X before it's declared. So if you're going top down in your file, it has to be top down, and names have to be unique. So I can't have two functions named add in C. I can't do this and have them be different. It does not understand that. One more piece. Capitalization matters. This would be fine because capital A add is not the same thing as lowercase add. And this is also bad because we're telling the programmer we're adding, but we're really multiplying. So, you know, don't do that. If you're going to multiply, call it multiply. So yeah, basically those are all the pieces of C you need to build a program. Your primitive types are all here. Here's how you declare and assign values. Here's how you declare and assign function. Here's how you declare a function and or define it, right? So we can declare it and define it in two different places if you want to. but the names are for you to understand what's happening in the program. So be careful with your naming. I would probably go to this year, blah, blah, blah. For kids under 10, that coding language, what would you teach? I would teach Python. Nope, I would still do C. My biggest problem with JavaScript is the missing type safety. Oh, there's so many problems with JSON, with JavaScript, though. Another example is the lack of a proper integer type. Always fun. I probably would go to C#, but that's just me. C# reminds me too much of Java. It hides... Okay, if you're teaching... Again, depending on what you're trying to do. If you want to be a game developer who uses Unity, C#'s great, right? Because that's what you would do everything in anyways. But C# has the same problems I have with Java. It hides too much from the programmer. You have a lot less control over what's allocated when and what's freed when. You have less control over that loop. And you don't have to think about your memory as much, which once you learn to manage your memory, yeah, sure, go use C# because you'll know how to avoid the major pitfalls. But for a beginner to not think about where their memory is coming from and where it's going to, it delays them starting to pay attention to those sorts of things. What's on the stack? What's on the heap? When was that freed? You don't have to. It works fine without. Yeah. Like I said, I think C# as a secondary language is fine. I would still start with C. I would go C# too, since it has a pretty nice UI toolkit. Can make desktop app easily for fun instead of for boring console. See, I just went to Qt and kept with C++ for my GUI toolkit. You can go to Unity easily. Yeah, if you want to go to Unity, C# is a great place to start. You should. Yep. Are we at pointers yet? Oh, we are going to do pointers. Probably not today. Well, no, we'll avoid pointers today. We'll talk about those more. Like I said, we haven't really covered the stack or the heap or allocation or freeing memory. So we'll get to all that soon. I think the more you have to teach someone before they write and see working code, the harder it will be to get the person interested in coding. Yes. But I also don't want to create a situation of, here's a blinking light. You made things, blink. It's like being in a casino. Hey, look, shiny thing. 99% of programming, your code is broken, and you're looking through the text for one tiny little thing you did wrong, and it's about being bullheaded, stubborn, ornery to let a bug beat you. So if you train people to respond to low input stimuli, that is different. Like programming, you can get interesting outputs even just on a console. My goal is to get someone interested in coding. Yep, that's a different goal. I don't know. Like I said, it all depends on goals, and I'm not sure that the order I'm teaching things in right now is the best or the right. I'm trying to point out things that aren't often taught to beginners. So, and again, I think I have to go through this lecture a few times to iron out all of to be like, oh, here's where I should have explained more about that. Here's where I should have explained more about that. Here's something I didn't have to talk about quite so early. Programming is so broad and so interconnected. It's kind of hard to know all the right things. If I was teaching kids, I would probably approach it very differently. But my nephews are teenagers. They should be able to handle a little bit of light math and get started with that. So let's see. Where was I? Yeah, the short answer is choose the tool that best accomplishes your goal. Let's see how to make a function. How to learn a new programming language. You need to find a good source of documentation. Here are some good C references. We kind of talked about those already. I prefer C++.com over the CPP reference most of the time, but there are good things here as well. Then what you need is a problem to work on. So we've got 5-ish programming problems that we can work through, just so you can see some code, right? And I'll let chat pick one. It doesn't really matter which one. A lot of these should be for an advanced programmer or even an intermediate programmer. Should only take a few minutes to solve. and we'll just pick one and work through it. So you can kind of see the elements I'm talking about. Here's your primitives. Here's how you combine them. Here's how you do the ifs and loops and things like that. And we will talk about all of those. I think in the future, this lecture needs to be broken up into 2 parts. I think I need to go into more depth in a couple of areas and break it into 2 chunks, but we will start one of these problems. Convert hours, minutes, and seconds. All right, good choice. We will work 1 or 2 of these and leave the rest as an exercise for anyone who wants to work on them. Okay. Whoops. Don't do that. Throwing too many data types at once at a new coder could overwhelm them. Yes. Yeah, which I think is why I need to spend more time in the first half of this lecture as a separate piece. It's all in flux. This lecture will get better as I refine it. Okay. So we're going to convert hours, minutes, and seconds into just seconds. Let's do this. Let's make a new file that's not cluttered. We're going to call it hours, minutes, seconds, 2 seconds.c. Okay? You can name your files anything you want. I have not taught an Emacs thing, so maybe we should do this in Notepad++, just so you know that there's nothing magical happening. We'll do that. We'll do that. Reload. Okay. Main. Let's open hours, minutes, seconds. Where did it go? That's ugh. Who designed this crap? Desktop. There's main.c. Can I not save HMS? There it is. We'll open that. Okay. We know we are going to print out stuff, so we should start with include stdio.h. I've already told you I tend to prefer using my integer types more defined, so stdint.h is not a bad place to start. Main is a special function. It always returns an integer, so we should make sure we do that. And last time we talked about returns 0 is the default for main. That means no error happened. That's by convention. You can return anything you want, as long as it means something to you, but by convention, 0 means no error. Okay, and then, as always, we start with a good old printf to make sure things are running and we know what's going on. Hello world, exclamation, backslash n. Okay, so we have a code file. I'm going to bring up a command line. Again, this is outside of my IDE world. You don't need fancy things to program. We'll get to more fancy things as we go, but we're going to start with the bare bones. Where's command line? I thought I had that showing before. I don't. Why is it not showing it? Oh, there we go. There's my command line. Okay. So we're going to do gcc hours, minutes, seconds, 2 seconds.c. And we talked last time, the default output is a.exe or a.out if you're on Linux. We can tell it what to output. So -o or -o means output something named hours, minutes, seconds, 2 seconds. .exe. So instead of a.exe, it's going to output this. We run it. Now we can hms2.exe, and it runs. There's our hello world that we told it to print, just like here. We're good to go. Okay, main function, we want to put something into the program. So we're going to take int argc star 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 argv. We'll talk about what these mean. Oops, wrong editor. But what we're going to do is, we're just going to talk about this. When we run something on the command line, we can put additional commands after it, parameters after it, right? So GCC, here's one of the things that goes in. It's the name of the file to compile. Then -o is an argument that says, hey, I'm going to tell you what to name the output. And then here's another thing. So these are called arguments. So argument C is the argument count, the number of arguments that have been called. So if I ran this, argc would be 1, 2, 3, 4. Let's just do this. Let's 4 int index equals 0, index less than argc, increment index. We'll use one of the plus equals for now. So 4 is the loop. It says starting at index 0, and as long as the index is less than our number of arguments, increment our index. Printf argv, argv subscript index. Okay. Isn't the exe named the first? Maybe I'm smoking though. As long as it's -o, it's just the next parameter. So I think we can do this hms2.c, and it should still work the same. So if we run this now, it did not compile there. Interesting. What did it do when it compiled then? No, I meant in the main function. I thought it includes the program too. Yes, it is. So that's why I was going to print this out so they could see what's going on. So if we build this and then run it, where did it go? That's still hello world. Why is that still hello world? Oh, because I haven't saved it. It's unsaved. Now we compile it. Wrong one. This one. So the name of the program is the first argument always. Nice. Some mini lectures. I assume these will end up on YouTube? Yes, and a new playlist called Beginner Programming or something like that. Ask AI what are the most common coding languages taught at most colleges. They said according to current trends, the most common coding languages taught at colleges are Java, Python, C++, JavaScript, and SQL. Why did they put that as a programming language? Gosh. With Python often being the preferred introductory language due to its simplicity and readability, while Java remains popular for its versatility across various applications. Yep. But that's... I argue for a serious computer science student, C is still the best place to begin. Don't ask why with AI in the same sentence. Exactly. Maybe we'll get around to the AI lecture next week. Why AI will not replace me as a programmer, not in its current form. Yeah, no, I know Python, Java, JavaScript, C++ are all very common languages to teach, but I don't think it's the right way. I think C is the right way to start with someone who wants to be serious about programming. Which may be after they've already done it as a hobby, right? This is distracting. There we go. No. Okay, so if we wanted to pass more things to this, we can do that. So we can say, hours 5, minutes 33, and seconds 12. And it'll say this is the argument 0, argument 1, argument 2, and argument 3. That's what we've done with this loop. Okay? So now we need to include stdlib.h. I'm pretty sure that's where it lives. So what we're going to do is say if argc is less than 4, means you're using our program wrong. Printf usage hours minutes seconds 2 seconds .exe, and then hours minutes and seconds. Otherwise, we do something else. So this is part of that branching we were talking about. If this condition is true, then that. Otherwise, int hours equals argv. So this is a string at the first index. And we use a to I. That's alpha to integer. And that is going to take the string we pass in here and turn it into an integer. If I could spell it right. Now we're going to do the same thing for minutes. A to I of argv2. So the next one. And I keep using the keyboard shortcuts from my usual development environment, so I'll have to stop that. Seconds. And that equals a to I, so alpha to integer of argv3. So this is an array of arrays. It's using double pointers. We'll talk about what those mean later, but for now just know that argv subscript and number gives us a string, and then we turn that into an integer. Okay, it's one of those built-in functions. So let's print those out. And we use %d to tell the compiler to print out an integer. Hours, minutes, seconds. There. So that should output what our inputs are as integers. So let's do that. Let's compile and run. Uh-oh. I forgot the semicolon. See that? Tells me right where to go. No semicolon. Put it in there. Save. Compile. And run. Usage. I didn't give it any arguments, right? I told you you need hours, minutes, and seconds. So if we do that, we'd say 5 hours, 33, and 12. 5 hours, 33. If it did something wrong, it's because I told it to do something wrong. Minutes. Then we recompile. Then we run. There we go. Hours, minutes, and seconds. Just exactly what I'm talking about. If you tell it to do something wrong, it will do something wrong. It is not smart. It is not intelligent. It only does what it's told. Now, it can be very clever telling a program what to do, but ultimately, it's not very smart. Okay, so we want to turn these three into a total number of seconds. So we need a total seconds. Now we're going to add the seconds. We don't have to do anything with seconds, right? But we need to add the seconds from the number of minutes. So minutes times 60, right? There are 60 seconds per minute. Then we have to add, whoops, come on. The number of hours worth of seconds. And there are 60 minutes per hour, and there are 60 seconds per minute. This is a very simple program. Compile it. Okay, coding language I use the most is PHP. Yep, I touched PHP way back in the day. Used it a bit myself. I would not say it's a beginner-friendly language. Again, unless you're doing web development, it's really not useful. What happened here? Oh, and I mean command line instead of bash. Printf total seconds. Oh, modulus D. Again, I told it to do something wrong, and it happily did the wrong thing. What is going on? GCC HMS -O. I feel like the key is stuck here. HMS 2.C -O HMS. Why would it do that? I feel like the control key is stuck or something. HMS 2S.exe. Huh. Yeah, I think my control key is stuck. 2S.exe. There we go. Total number of seconds. 19,992. We can pass it any number of hours. -2 hours. Plus 33 minutes plus 12 seconds. It'll do it. Even if it doesn't make sense. Right? So if we're doing like marathon running times, negative numbers don't make any sense, right? But I didn't tell it to do anything besides that. So that's what you get. You want to add the minutes back in. You want 1 hour, 33 minutes, -12 seconds. It's up to you. So there you go. That's a very, very simple example of using an array to use a built-in function to assign a value, using a few operators to do some math, and output an answer. So very, very simple stuff. Maybe we have time for one more example problem. Putting it again to the vote. No, that command line is right on top, isn't it? There we go. All right, practice problems. Again, I'm going to leave some of these as an exercise for people to actually work through. I just want to show like examples of code using the pieces of C that we've talked about. Anybody? What's this? Oh, well, we could do the other way around. We could do the bonus. That's not really complicated. Checking for palindrome. Count character classes inside of a string. All sorts of things. I'm trying to think what I want to do here. Maybe did you introduce loops yet? Yes, we did. We talked about them. We can talk about them some more. Because I think I only used the for loop. So let's talk about, let's clean up some of this. That scratch file is a little bit crowded here. Okay. In C, you have a few different loops. You have a while loop. While some condition is true. You have a for loop for initialization, initial condition, semicolon, end condition. And you have the step. You also have a do while, which is one of the things I very differ strongly on with Python. Oh, I've got things hidden and showing. Browser, go away. Notepad, go away. There we go. 4 is the best while loop. Yeah, no, I've used them all. I've used them all. That's most of your loops in C. So one thing we can do is while true. Well, that will go forever. This is called an infinite loop. Or we can do any other test, like if x is less than 10, right? So we can declare x equals 0. X is a thing. X is plus equals 1, right? Maybe we do something like that. Let me do some work in here. In fact, we can just do it. There you go. So that'll print all the numbers from 0 to 9. If you want to do it here, x equals 0, print f number x plus equals 1, while x is less than 10. That should do the same thing. So the difference between a while and a do while is that the do always does this thing one time no matter what, and then checks if it exits, whereas while checks if it exits before it even starts once. So you're not guaranteed that this will work. If I say x less than 0, this won't ever print anything. If I set this to 0, this will still print that first one no matter what. I use things like do while for things like menus. If I expect user input, I will expect the user to input some things, then I'll check and see if the inputs are valid. Otherwise, I'll go back to the top of the do loop. So I'll break out of the loop if the condition is met. So while, do while, and for. For for, we might do something like this. For int index equals 0. So I'm declaring an index, setting it to 0. I'll keep going until our index is greater than 10 or equal to 10. So as long as the index is less than 10, then index plus equals 1. This is not a comma. There we go. These are all similar. I haven't used do while in 20 years. Oh, let's see here. You're missing one loop with go to. Oh yeah, go to. Go to. 2 more loops. 2 more loops. Do while, forward. Go to is an option, one which we're probably not going to address. And I'm missing a loop, I'm told. Which one? While input equals read is what I do. Well, so for example, if I want user input, right? Int user choice equals -1. Do user input user choice equals get user input. If user choice is greater than 0 and user choice is less than something, you know, the number of options you have, then we'll break. That's the usual way I use do. Or, well, this would go in all user choice is less than 0 or greater than the number of options. But yeah, it's every once in a while I really want to do while, and Python doesn't give it to me, so that's very sad. 2 more loops. While, do while, for. Maybe in the future you'll teach a new coding language as a beginner coding language. Maybe. Yeah, I don't know. I don't know if my language will be particularly user friendly or beginner friendly. We'll see. Okay, so we've talked about loops. While, do, while, for. In C, that's all the loops. There is technically a go-to. In C++, there is a for each loop that's a little bit different, but we don't need to talk about that because we're not doing C++. Just thinking about how you can change the instruction pointer. I mean, I can do go-tos to loop, but that's not something I would really teach a beginner. I can do other things in my loop, but it always is, let's see. Is there a map in C? What kind of map are you talking about? Like a dictionary lookup map? Or a map, a general map operation for applying transform to a collection? In C, there are neither of those. Recursive function calls. Oh, yeah. I did know that. Recursive function calls are a kind of loop if you want to use them that way. That's fair. Map look method. Hash table? Nope, not in standard lib. Not in C. Yep. I would not say that counts as a loop. Yeah, but you can do it. I don't know if I want to address that this early in a beginner's course. Like, this is kind of me just taking a stab, throwing a bunch of material out there and seeing what works. I don't know if I want to hit recursion on lesson 2. I already want to break lesson 2 into 2 parts. Map loop method. Nope, there is not in C. There is not in C. Go to recursion. I mean, yeah. You can loop with recursion. That's not really why we use recursion most of the time. Anything that's trivially loopable with a recursion is better done using other methods of recursion. We use recursion more for structured data hierarchies. But anyway. But we can mention it. It's not that bad. Yeah, no map loop method in C. Okay. So let's do one more quick example problem. Which one did I settle on? Did I settle on one? Yeah, already I'm seeing places where I need to change the old. Oh, on it. Lost my mouse cursor again. OBS does not like it when I. Sheesh. Okay. Recursion can accomplish looping like behaviors. I don't know. So for the beginner programmer, recursion is when you use a function to call itself. So it'll call itself over and over again. You have to be very careful not to overdo it. It can blow up your program. You have to clear exit. We'll talk about all that eventually. Maybe it's me, but the more experienced you are, the more you stay away from recursion. Well, you basically just use recursion for hierarchical data structures, right? You want to walk an abstract syntax tree in your programming language. That makes perfect sense. You recurse all the time. But yeah, I don't use it for anything fancy. Yeah. Well, it's kind of like templated programming, right? If you go into C++, there are some bizarro things you can do with templated programming, but I'm like, the longer I go, the more I'm like, you know what? Only for containers. I will only use templates for containers. I'm not going to use this everywhere. It's actually one of my big complaints about like things like GL math and whatnot. It's all hyper templated and just a pain to read through their code at all. Yeah, recursion's a tool. It has its place. Can be overused and abused. Let's check for palindrome. Let's check for palindrome. I think we'll do that. Pure functional programming uses recursion only. Yep, but I don't use pure functional programming. The only time I would use pure functional programming would be something like a Lisp, which already has looping structures as macros anyway. So you don't have to interact with the recursion at all. Yeah, once they figured out the Y Combinator, then your lambda calculus all can be branched, and then you have your recursion. It's all very complicated. Okay, so let's just do one more. Let's do one more quick example program. Check if a text is a palindrome. No, we'll leave that one. We will leave the text as a palindrome. What should we do? What should we do? Let's count consonants and vowels. Consonants and vowels. Consonants and vowels. Dot C. Okay, we know we're going to want to output something. We want to output true or false. So stdio.h comes right in. Int main, we know that we need to take some arguments on the command line. Int argument count, and then the string vector is there. And if argc is less than 2, so we expect the first arg is the name of the program. The second argument is the string we want to test. If arguments are less than 2, you're not using it properly. So we will printf usage consonants and vowels .exe text. Tell people that they want to put text in. Otherwise, we do a thing. We want to count two things. We want to count how many consonants. Consonant count. I'm going to start at 0. And then we're going to output a vowel count. And we know that the next thing we want to do is get a string, which is really just, let's do this. String.h. Character, pointer, let's see here, text equals argv1. So argv1 is the first parameter, the first argument being passed in. We're going to save that into a variable called text, so I don't have to keep typing argv1 over and over again. And now we're going to use a built-in function for int index equals 0, index less than string length of text. Index plus equals 1, and there we go. So this is going to take text, which we've passed in, and it's going to step through every character starting at character 0 all the way up to the last character of text. Okay, strlen walks through the text looking for a special character that means that we're at the end. And that special character is 0. 0 in ASCII means end of string. Okay? And that's how C has their strings. It's an array of characters that ends in a 0. And then we're going to step forward through that. So that's all we're going to do. So we could literally, for now, printf character at index is that character. So we can use index and text at index to get our character. Okay, does that make sense? Did I close the shell? output as consonants and vowels.exe. Consonants and vowels. It should tell us we're using it wrong. We should put backslash in here as well. Rebuild. Run it again. Consonants and vowels.exe. I need to pass in a text, so we do. We say howdy. Character 0 is H. Character 1 is O. Character W is 2. Character D is 3. 3 is D. Character 4 is Y, and then it stops. Perfect. So it's working. So what we want to do is say if our character, so let's get a character, C equals text at the index. If C equals a vowel, right? So A or E or I or O or U. And I'm going to do this wrong on purpose, so all of you experienced programmers, don't worry about it. Oh, this is dirty procedure programming, mind you. Yes, yes. Well, you know, more and more I like procedural and structured programming paradigms these days. More and more. Simplify, simplify, simplify. Then the vowel count gets bigger by 1. Okay? Otherwise, we have to do something else. We're just going to go ahead and improve our consonant count by 1. And then at the end of that loop, printf vowels consonants given the vowel count and the consonant count. This is wrong. It's not a correct solution. Oops, I'm autopiloting here. Oh, and I'm doing it in Emacs. My autopilot is so strong. Haskell, Erlang, Elixir, functional programming languages. I heard Haskell was built as a programming language to teach students about functional programming. Yes, but you already had Lisp. I don't know what Haskell accomplishes that Lisp doesn't or can't. Lisp is, yeah, I don't know. I suppose Haskell is more interested in solving, I don't know. Yeah. I've looked at some Haskell and I'm not really bought into it enough to want to teach myself it. Designed for teaching, research, industrial applications, Haskell's pioneered several programming language features such as type classes, which enable type-safe operator overloading and monadic input-output. It's named after logician Haskell Curry. Yeah. But those aren't my problems. Those aren't what cause me suffering when I code. So it's fixing problems I don't have. Does that make sense? I'm going to hide Emacs because I automatically went straight to Emacs. We're going to show Notepad++. You don't need anything fancy. We'll load it up in here. Open. Consonants and vowels. There we are. Same code, different editor. Doesn't matter. Let me get my command line back up here. Command line, here we are. GCC consonants and vowels -o consonants and vowels .exe consonants and vowels .exe. Okay, I still have to provide a text. So howdy. I would expect one vowel. New line characters killing me. That's one of the first things I do is we'll get around to that. That's later. Howdy. Oh, come on. Didn't build it. There we go. And there we go. One vowel, 4 consonants. That is technically correct, but our test case is too narrow. Sounds like GPT wrote that. Yep, it does. They definitely do, but that's a huge discussion. Yes. You for sure missing type classes. C++ concepts aren't quite as good. No, C++ concepts are not as good. Okay, so let's try this. I'm telling you right now, howdy is going to fail because there's a vowel we didn't count for. An uppercase character and lowercase character are not the same thing. So we have to check for uppercase vowels. All right. I, O, and U. And we have to check uppercase and lowercase. So now we have even more conditions to check with our ORs, our logical OR statements. Let's try that. And we're going to check this howdy. That still works. And if we do it with capitals, that works. All right, let's do this then. Let's do our hello world. If we put it inside of string quotes, boom, 3 vowels. So E, O, O. That's correct. Consonants 1, 2, 3, 4, 5, 6, 7. Because of the way we were thinking about our problem, we didn't think about this space. Oh, shoot. Darn. Darn, we say. Well, we're going to have to check for that, aren't we? So, one way we could do this, are you ready? Is to suffer. We could say if C equals B or C equals B. Or, and we can check every consonant as well. I don't like that. So we're going to cheat. We're going to say, I want a character array called vowels. And we know how many vowels there are. There are 5 vowels. And we're going to say A, B, C, or A, E, I, O, U. Good heavens, what am I doing? A, E, I, O, and U. Just like that. We can do this. We can declare an array of 5 vowels and just give it that. Probably better. Has anyone heard of a coding language called C with classes? Yes, I have heard of it. I have very little interest in it. A reasonable subsection of C++ covers it okay enough. We need to know how many vowels. And then we can use this here. So for the beginner, this is const. It means once I set this value here, this integer number 5 will never change. Which means that this number is always fixed. And we can do the same thing for consonants equals 26 minus 5, which is 21, or 21 consonants. Consonants. C with classes was the first name for C++ as far as I heard, isn't it? I think, have they forked it so that it's kind of its own little thing now? B, C, B, E, F, not E. What am I doing? G. We need 21 of these. G, H, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y. No, I don't want full screen. Why did you do this to me? I don't want full screen. There we go. Type classes. There, that's all the consonants we have to worry about. We could put the uppercase and the lowercase together, but we're going to do one clever trick that'll fix it. So here, when we have a character, instead of checking every one of these values, we can do this. For int v index for vowel index, or letter index. Our letter index is less than the number of vowels. Letter index moves forward by 1. C with classes is a dialect of C++ 2011 used in this course. If the character equals vowels at our letter index, or if our character equals uppercase, do I have to subtract or add? I look at ASCII. I need to look at an ASCII table real quick. Uppercase and lowercase. So I subtract. I guess it doesn't matter. We can do this with just simple arithmetic. Minus the difference between capital A and lowercase a. Easy to learn for Java developers. To that end, CWC encourages a programming style that emphasizes class-based programming with dynamic dispatch, expose developers to manual memory management. Students are faced with design choices between stack and heap allocation, must be hygienic in their use of memory. They talk about C++ and I have no idea what they're talking about. Yeah, C++ has moved well beyond that that time, that era. Okay, so what are we doing here? The difference between capital A and lowercase a is the same difference from any lowercase to its uppercase equivalent. And so we can take C equals the vowel, or C equals the vowel with that offset. It means we're checking the lowercase and we're checking the uppercase version. And we can do the same thing for consonants now that we've set it up this way. The number of consonants, we just check the same thing here, and that is the consonant count plus 1. And that should just about do it for this one. So let's build excess element. BCD, did I put a vowel in? 1, 2, 3, 4, 5. 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 6. That's 21, right? There. Variably modified vowels. Do you have to make this constant to make it go away? Meaning I promise I'm not going to modify it. Okay, they don't want me to declare that. I can't. That's odd. I thought I'd be able to initialize an array like that. No, we can use the string. I don't like that I'm being forced to use a string here. Shouldn't have to. All right, so here's the dirty secret. In C, a string is just an array of characters, but you use double quotes instead, and you don't have to use the curly braces. So this is still just an array of characters. Not sure why it's complaining about me initializing an array of characters that way. It shouldn't be that difficult of a chore, I think. Alright, well, we'll treat it as a string then instead of what we were doing. I actually find that a little disappointing. This Barney Strip marketing team, when he did C front and stuff, I don't think C with classes was still relevant after C++ became nice. Yeah, C++ was when it took off. He needed that rebranding for it to work out. Vowels at L index not equal to the end of string character. That's really the only difference here. Try building that. And then running it. There's our howdy. It did not work. Why did that not work? Let's simplify. If you have a problem, you just comment out other parts and simplify it. So we get our character and our text. That's fine. We get our letter index. As long as our vowel at letter index is not the end of that. Letter index plus equals 1. I prefer using CWC than C++. C++ has some serious issues. Vowels. Oh. Well, that's one problem. Anyway, vowel count plus. That should have worked for the letter O. There's the letter O. Okay. Flip those around, it should be fine. There it is. Just add the math backwards, consonants, lowercase, uppercase, and build and run. 8. That's a lot of consonants. Oh, so I added an extra one, duplicated. If you tell the computer to do something wrong, it will happily do it wrong. Do you use std vector or template? I try to stray away from them more and more as I go. There are times where templating is completely appropriate. Personally, C doesn't have classes. blah, blah, blah. Save. One and 4. That's correct. And it doesn't matter if it's uppercase or lowercase. Should work the same. Now, hello world. We would expect 1, 2, 3, 4, 5, 6, 7 consonants and 3 vowels. Perfect. So there we go. We've done it. Yeah, I didn't want to get into strings that much, but here we are. We'll have to talk about strings and what they mean in the future. Okay, so we've worked our way through 2 of the different puzzles, hours, minutes, seconds to total seconds. And here, kind of the same thing, right? We declared some values. We said these are constant, which means you can't change them. It's an array of characters. And we use the C string syntax to define it. We check our value. We set up some initial conditions, get our text string, walk through each character of the text string. If it's a vowel, right? So here's our loop. Check each vowel. Are we equal to the vowel or the uppercase version of the vowel? Then we can add 1 to the vowel count. If we're in constants, we work through all the constants and say consonants rather, and check and see if we're in the consonants or equal to the consonant offset by the uppercase to lowercase difference, and add that. Then we print it all out. So again, we're using some simple primitives. We're using an array. We're using some built-in functions, some built-in operators, some looping, some conditions to solve a problem. We have to break each problem down into little teeny pieces, decompose it, and then find a sequence of steps to execute with branches and loops to get it done. And now we could pass it really long strings and it'll count it all up. So we can pass in all sorts of things. Let's see here. He was born with the gift of laughter. And it will just count them up really fast. This is why we like computers. If I had to sit here and hand count these, it would take me forever. But it just, boom, happy to blow through a list. It'll count for a whole book's worth if it wants to. So some simple, basic C. There are still some puzzles if you want to work on those. We'll finish up here. So close out these. Just close it. There we go. Back to the old browser. There's other practice programs. You can do the bonus sections based on what you've seen. I'm not going to post this code anywhere. I think it's better as a beginner to enter the code yourself and work through your own programming bugs. Like start seeing those command line bugs. It's better to do that than to copy paste someone else's code at this point. As a beginner, it's about time spent programming and debugging your own programs. So you can check to see if the text is a palindrome. That's a great starting one. You can copy what I did above by typing it in yourself and then expand on that bonus one. Or you can write a new program that uses the same ideas from here to take in a total number of seconds and then convert it into hours and minutes and seconds. The Josephus problem is a good one for building an array and walking through it. You'll have to read through a bit, and we can talk about it if you're interested in working on the problem. Maybe I need to rephrase it from what's in the Wikipedia a little bit. It's walking around in a circle and killing people in a circle. Yeah, so plenty of small programs to work on. Any advanced programmer is going to take not very long to go through most of these, but a beginner would struggle to get through the decomposition and building up that sequence of instructions that'll work. But yeah, if you have any questions, let me know. I definitely think I need to restructure this lecture a bit and do things differently, but I will post this video and the slides to YouTube for general consumption after I clean up a couple of typos. So let me know if you have any questions. Otherwise, we're going to wrap it up there. And tomorrow we'll start a slightly different tact. We'll see where we go from there, but we're going to talk about models and how to think a little bit more and start a more significant project size, one to follow along with. Yeah. So everyone have a wonderful evening, and I will see you tomorrow for another beginner programming lecture. Bye-bye.